Hello everyone, I'm Xiaoqi. Welcome back to the channel. Today's video is a direct continuation of what we discussed in our previous episode. In that last episode, we introduced exactly what FlyCore is, and we also assigned a specific task to complete. To build an intelligent drone in the shortest possible time. In order to create this advanced drone as quickly as we possibly could, we made extensive use of some powerful AI tools, leveraging the power of AI and our specialized FlyCore motion control board. As long as you are genuinely willing to learn, any creative idea you have about drones will eventually become well within your reach. Okay, let's get started. In the middle, we have the outer shell that we 3D printed in advance. Over here is our FlyCore. These are two RTK antennas. This is the LiDAR, and here is the vision sensor. You can see below is the flight controller. This is the IMU of the flight controller, and further down is the flight controller board. Here is the video and data transmission module, and this is the remote controller. Here we have the smart battery, here are the propellers and motors, the arms, and some screws. These are all the parts and materials we'll use to assemble the FlyCore. So let's start assembling. Alright, now the frame has been completely and meticulously assembled, and now we're mounting it onto the main frame. In fact, this entire frame was designed using advanced AI, which has saved our engineering team a truly tremendous amount of valuable time in the overall design process of our drone. Now we just need to carefully snap the top cover into its place and proceed to install the FlyCore components exactly like this. Once that is finished, we can see that about 50% of our total assembly work is successfully completed at this point. Okay, it took us about 2 or 3 hours to completely finish the assembly process. Now that we've successfully completed the entire assembly, we're going to do a power test to see if the baseboard and the onboard computer are powered correctly. Okay, all of the onboard lights are working as they should be. Moving forward, we are going to begin the essential process of software debugging and development work. Remember, our ultimate objective for this project is to have AI fully take over the operations of this drone and utilize AI to drive its further development. Now we have 3 specific tasks to complete next. The very first thing is to establish a stable connection to the QGC, and we'll verify its current operational status and telemetry. The second thing is we will enter the x86 system's web operation interface. This way, we can see the specific status of the entire system, as well as the interaction of our FlyCore positioning system. Then, our ultimate goal is to let the AI take over control of this aircraft. Alright then, our remote controller is already successfully linked. The network port is connected to a router, and the computer also needs to be connected to that same router to ensure that all 3 devices are on the same network segment. Now, as you can clearly see here, QGC is already connected. So how can we connect to the QGC? In fact, our wiki documentation explains this very clearly. In practice, it's just like this. Use UDP mode to listen on port 8080, and it will easily connect to QGC. Now we move the aircraft. We see the attitude changing in the right of the bottom. The top left shows ready to fly position hold, meaning it's ready for takeoff. You can also see the battery level. Since it's a smart battery, it's monitored precisely. Now, log into the onboard computer via remote for mapping and positioning. When we log in, we can see that this is our Fusion Positioning BSA SLAM. This algorithm runs within a web-based interactive interface. Next, let's take a look at its current positioning status. Here, there's an icon for the spatial coordinate system. Let's click to open it. It will then display the current spatial coordinate system. Let's move the drone a bit and see the specific positioning situation. Okay, we took the drone for a spin in our area, and now we can see the interaction on the web. It has now returned to its starting point, and its X, Y, Z axes have also returned to their positions. The full path is now on the web interface. In fact, we only moved around in a few specific and limited areas of our company, a few corridors plus a small section of the public area outside, and it was all displayed completely. As I just mentioned, we will use AI to assume full autonomous control of this drone. This will be a key part of our future development work. Not only can it greatly improve our overall development efficiency and productivity, but it will also allow us to experiment with developing a wide variety of different functions. We will also try something here. using AI to generate a web-based ground station in the shortest time, then be used to control the takeoff and landing of the aircraft. Now that we have successfully connected all of the components, we are going to configure and adjust some essential parameters and then use Cursor to take full control of the drone. Now we set up and configure passwordless access for remote server login. Okay, Cursor has informed me that it can achieve password-free login, so let me perform a quick verification right now. We command it to set up the ROS 2 environment for the RK3588. Okay, that is very fast. It has already automatically installed ROS 2. Now let's try having the AI write some functional code. Our specific coding requirement is that we have a custom algorithm that needs to read the incoming laser point cloud data and the precise position data from the mapping and localization software. The algorithm is running on the x86 system and the results are obtained from the mapping and localization algorithm. Then the RK3588 will obtain the incoming data. We've prepared a sample source code and now we're going to demonstrate and provide this sample code to it. Let it write a ROS node from the sample. Okay, the AI has completely helped us write the code, which actually took a fair amount of time. Now let's take a closer look at the code. Open up a new terminal and there are a total of 3 different topics. The first topic is the position data, the second is the point cloud data, and the third is the ODM data. Let's check right now whether it can correctly read our specific position data. By the way, this entire step is being carried out on the RK3588 hardware platform. We can use the echo command of the ROS 2 topic. You can see it is printing out the position information in real time and also includes the XYZ values. We maneuver the aircraft in various different directions. We move the aircraft in different directions. When we move forward, you can see that the value of the x-axis is changing. When we move backward, the value of the y-axis is changing in the corresponding direction. Now, as we move upward, the value of the z-axis is also changing accordingly. This all seems perfectly fine. Now, let's return to the origin. What kind of change will it have? Maybe the data on all 3 axes will basically reset to 0. That's right, we can indeed see that's the case. The final result that we see here should be identical to the data output by SLAM. This proves that by using AI, we were able to efficiently and very rapidly complete complex tasks like setting up the ROS 2 environment. In fact, what we did was provide it with a specific segment of driver code and then allowed the system to autonomously handle the parsing. Once the parsing was successfully done, it shared the data in the form of ROS topics. In this way, our overall efficiency was significantly and noticeably improved across the board. If we had to do this kind of complex work in the past, I estimate it would have taken us at least half a day or even a full working day to do it. But now, we only need about an hour of our time, or even less than that, roughly 30 to 50 minutes, to successfully complete the entire process. It is truly a remarkable shift in productivity. Okay, next, let's continue our demonstration and use the power of AI to take over the operations of this drone. We are going to have the AI write a web-based ground station interface to control the drone takeoff and landing.